Hi, my name is Zachary Lyons, and today I'll be presenting the lab number 2 Charged Tapes Revisited Lab for Physics 2212 at Georgia Tech. In this lab, the goal was to prepare two pieces of charged clear tape as we did in Lab 1 and determine their interactions between them. And then we were going to determine the amount of excess charge on one piece of the charged tape. However, for this lab, we're going to consider the tape as having its charge uniformly distributed across its length rather than it being a point charge. And we're going to simulate this computational model in VPython. The findings were that the charge tape still had a net positive charge as in Lab 1, and the charge of this tape was 3.0542 times 10 to the negative 8 coulombs, and the tape was deficient of 1.9 to the negative 11, 10 to the negative 11 electrons. Some key concepts for this lab are Newton's second law, which states that the net force on an object is equivalent to the change in momentum over time, and the force of gravitation, as shown by F equals negative mg, and with g being equal to 9.82 meters per second squared. The electrical field for a rod with uniformly distributed charge is shown by this equation here below. This equation is used to make an approximation for the charge of the tape for this lab. Since the tape must have its charge uniformly distributed across its length, we need to consider the length of the tape in this calculation. The electric force shown by Coulomb's law is shown here. We also need this in our computational model, and it's equal to the product of the Coulomb's constant K and the charges divided by the distance between the charges squared, multiplied by the unit vector r, and r hat points away from the source of the charge to the point of observation. Some key assumptions for this lab is that the charge is evenly distributed along the tape. Therefore, we can model the tapes as a multitude of singular point charges in the code. We can also ignore air resistance, and both tapes have the same amount of charge. The procedure from Lab 1 is recreated for Lab number 2, where we suspended one tape and then brought the charge tape near it and observed the interactions. We needed to measure the separation distance between the U tapes, and that distance is the same as it was in Lab 1. The observations from Lab 1 were that the interaction between two tapes repelled, which means that we know that the tape must be positively charged because we brought a negatively charged pen towards it, and since they were attracted, as seen here, that means they're oppositely charged, which means that the tape is positively charged. The separation distance for this lab was 0.025 meters, which is about an inch. The free body diagram shown here, with the system being the suspended U tape. The forces are equivalent. It's in static equilibrium, so that means that the force due to gravity is equivalent to the electric force on the tape, which we can use to model our system computationally. Here are our experimental data and calculations, which were mostly from Lab 1. The separation distance and the length of the tapes were the same. The mass of the tape is the same, and the calculation for the force of gravity acting on the tape is the same. And shown here is the equation used to make the approximation for the charge on the tape as it's distributed uniformly across its length. And we found that based on the fact that the system is in static equilibrium. Here are the constants used in the computational model, with the separation distance being here and our charge being what we estimated using the equation before. And the link to the closed strip is shown below. Here is the computational model for the E fields and the tapes based on the equations that we were previously shown, where we have the magnitude of the charge here and the observation location minus the source. This is how we find our R vector, and then we can find the magnitude and R hat, so we can find the magnitude of the E fields. Then here is the computational model for finding the electric force on the object at the different points along the length of the charge. And the force vectors were created here, which gave the result of this, where the forces are equivalent and the E field could be seen pointing away from the charged tape, showing that it is positively charged, and it is in static equilibrium. And we can see that the forces are acting along the tape because it is a uniformly distributed charge. So based on our findings in this lab, the charges of the tapes were 3.0542 times 10 to the negative 8 coulombs, and we determined this based on estimation and the trial and error method in the computational model. The tape was deficient of 1.908875 times 10 to the negative electrons, and we know that since the tape is positively charged, there is an electron deficiency. And some sources of error for this lab were that the tape measurements could be inaccurate, as well as there could have been some rounding error. And if the tapes weren't exactly parallel, there may be some changes in the distances. So what if we had modeled each tape as a single point charge? Well, then the charge would be as it was from Lab 1. And for this lab, we see that there was a difference factor of 2.15 in the magnitude of the charge for the tape. Why do these estimates differ? And which is most likely closer to the real value and why? The differences are due to consideration of the tape as a charge distributed uniformly across a rod-like structure. The line charge models consider the length of the rod or the length of the tape, and the line charge is most likely closer to the real value since the tape is most like the rod structure. Thank you.